numerical methods, Newton's method, for instance, they give estimates, pretty good estimates sometimes.
The estimates aren't always enough, are they?
Exactly. They come with this inherent risk of rounding errors. They just can't promise exact values. And that leads to a big question in many fields. What if you absolutely need perfect precision?
Right. And this is where things get really interesting historically. For centuries, mathematicians wrestled with this. We even have Abel's theorem,
Ah, yes, Abel's impossibility theorem.
which basically states that certain polynomials, specifically those of degree 5 or higher, generally can't be solved using radicals, simple roots like square roots, cube roots, and basic arithmetic.
And that theorem has been a cornerstone, a fundamental barrier in algebra for a long, long time.
So it seems like we hit a wall.
Well, that's where Ezouidi's theorem comes in, offering a completely different angle. While traditional methods hit that wall or get limited by Abel's theorem for radical solutions, Ezouidi's theorem claims it can find exact symbolic roots. It doesn't actually contradict Abel's theorem, which is about solutions and radicals. Ezouidi's method finds exact solutions, sometimes involving things like complex exponentials, by revealing a sort of hidden algebraic structure. It lets us factor these complex beasts in a new way.
So it's not just approximating, it's finding the actual answers.
Precisely. It claims to deliver the exact solvable roots for equations we might have thought were effectively unsolvable in closed form. A fundamental shift.
Okay, so Ezouidi's theorem is positioned as this promising alternative, a systematic process that gets around the old roadblocks of classical algebra and numerical methods. It sounds, well, almost too good to be true. What's the core idea? How does it work?
Well, the core methodology is quite elegant, actually. The theorem lets us break down the polynomial piece by piece and solve for the roots symbolically. It uses a recursive process.
Recursive, meaning it refers back to itself somehow.
Exactly. Think of it like building something complex, but each step depends logically on the previous one. Here, we're systematically calculating symbolic coefficients. Each calculation refines our picture of the polynomial structure. It keeps going until the polynomial is broken down into its simplest solvable components. And because it's all symbolic, we avoid those approximation errors entirely. We get the exact values.
And you mentioned our specific 14th degree example. The source notes something interesting. X Caesars 1 is a root, and it appears twice. A root of multiplicity 2. How does the theorem account for that?
That's handled within the recursive process itself. The method starts by representing the polynomial using these symbolic coefficients instead of the huge numbers we saw earlier. The calculation of these coefficients is key. The formula conceptually uses things like binomial coefficients, terms that adjust the degree, base coefficients, and crucially, it references earlier terms in the polynomial as it calculates later ones. It's this recursive referencing that ensures we're always working with precise symbolic values, not numerical estimates.
Okay, and for this specific 14th degree polynomial, what did this process reveal? What did those symbolic coefficients look like?
This is where it gets quite neat. For this particular polynomial, the calculations show that most of those symbolic coefficients, they actually turn out to be zero. S0R, S1R, S2R, all the way up to S5R, then S7R through S12R, all zero.
Wow. Okay, so only a few are left.
Just two, in fact. The non-zero ones are S6R, which calculates to negative 3,000 times 14 to the power of 7, and S13R, which is 5,000 times 14 to the power of 14.
So wait, that incredibly complicated 14th degree polynomial we started with, it simplifies.
Dramatically. Because all those other coefficients are zero, the polynomial boils down to a much, much simpler form. Px equals x14 minus s6r times x7 plus x13r equals 0.
Hold on, x to the 14 point x to the 7, that looks almost like a quadratic equation, doesn't it? If you think of x7 as the variable.
Exactly, you can rewrite it precisely like that. Let y equals x7, then the equation becomes y squared minus s6r times y plus s13r equals 0. Or plugging the values back in. Plus 3,000 by 147 times x7 plus 5,000 by 1414 equals 0.
That's a huge simplification.
Oh, our listeners got something to share. Let's hear it.
This is a 17th degree formula.
Welcome to the deep dive, your shortcut to being well informed on, well, truly groundbreaking ideas. Today we're jumping right into one of mathematics' most persistent challenges. We're talking about finding exact solutions for really complex polynomial equations. And we're going to unpack a fascinating new mathematical. Oh, hey, I think our listeners got something to say.
Yeah, here we will see how the simple roots of this 17 degree formula equation will be derived with without an error estimation. Okay, meaning that we use the theorem of Ezouidi and we solve this 17 degree formula equation. 17th degree from equation, not 14th.
That's a great observation, and it really highlights what we're aiming to explore today.
Yeah, you zeroed in on a key aspect of Ezouidi's theorem.
You're right that the document mentions a 17th degree polynomial.
And it does indeed talk about deriving those symbol groups or coefficients.
And crucial to your point, it emphasizes doing so without any numerical approximation.
It's all about exact symbolic values, as you pointed out.
That's the power of this method.
For our deep dive today, we're actually going to unpack a 14th degree polynomial.
But the principles you just highlighted from the 17th degree example apply directly.
It's the same underlying mechanism for finding those exact roots.
Just with different numbers, but the approach is identical.
So your insight about the symbolic derivation is spot on, regardless of the degree.
It's precisely what sets this theorem apart.
Welcome to the deep dive, your shortcut to being well informed on, well, truly groundbreaking ideas.
Today, we're jumping right into one of mathematics' most persistent challenges.
We're talking about finding exact solutions for really complex polynomial equations.
And we're going to unpack a fascinating new mathematical breakthrough that might just redefine how we tackle these things.
The topic is Ezouidi's theorem.
This deep dive is all about giving you the essential insights into a potentially major advance.
It could really shift things in science and engineering.
Exactly. And our mission here is to explore how Ezouidi's theorem actually does it.
How it gets these exact symbolic solutions for polynomials that have been, frankly, incredibly tough.
Even for supercomputers.
We'll use a specific example, a 14th degree polynomial, to really see the theorem in action.
Understand its novel approach.
Okay, let's set the scene.
The problem. High-degree polynomial equations.
They've always been this huge hurdle, right?
So to give you a feel for what we mean, here's the polynomial from the source material.
P of x equals x to the power of 14 minus 14x to the 13 plus 91x to the 12.
I mean, it keeps going down to the constant term.
It's a monster, a 14th degree equation.
It definitely looks intimidating.
And the real challenge with that kind of complexity comes down to the limits of, well, the methods we've all